I want you to picture, just in your mind's eye for a second, a literal physical brick wall.
Okay.
Like it's towering, it's thick, and it's completely unyielding. And now imagine a high-speed bullet train just barreling right toward it at like 300 miles an hour.
That is a pretty terrifying image.
Right. But usually, when we talk about technology, and especially when we talk about artificial intelligence, we use all these, abstract, kind of cloudy metaphors. We talk about the cloud, we talk about data lakes, the ether, neural nets.
Like software-defined everything.
Exactly. We make it sound like computing happens in this magical, weightless dimension.
Yeah.
But today, in this deep dive, we're looking at how the most advanced, bleeding-edge artificial intelligence on the planet is hitting a very real, very physical brick wall. And that wall is the global power grid.
Yeah, the physical infrastructure is it's groaning under the weight of it.
It is. AI's hunger for electricity is completely outpacing our physical infrastructure's ability to supply it.
It's really a phenomenal collision of the digital and the physical, We've spent the last few decades in this industry operating under the assumption that compute power could just, scale infinitely into the sky.
The whole Moore's Law thing, right?
Exactly. We thought Moore's Law would always save us, that chips would just keep getting smaller and faster and magically more efficient. But the reality is it's strictly grounded in copper wires, transformers, substation capacities.
The actual physical town grid.
Yes, the unforgiving physical limits of local utility grids. Managing an AI superpod today isn't just about, plugging a server into a wall, booting up an OS, and walking away.
Right. It's way beyond that now.
It has become this monumental, almost terrifying balancing act of thermodynamics, highly pressurized liquid cooling systems, and frankly, millions and millions of dollars of silicon crammed into incredibly tight spaces.
So you're no longer just managing data at that point.
Not at all. You are managing a massive industrial power plant that just happens to process data.
And that's our mission for today. We're going to explore how the industry is trying to smash through that power wall by fundamentally reimagining the brain, the circulatory system, and the overall orchestration of the modern data center.
It's a massive pivot.
It is. We are looking closely at how Supermicro is navigating this exact crisis with their SuperCloud Composer, which you'll hear us refer to as SEC as we go along. And we've got a great stack of technical walkthroughs from them that we're using as our sources today.
Yeah, and it's important to note this isn't just some routine software update.
No, not at all.
This is a complete paradigm shift in how we build and manage these environments. Because as the power demands skyrocket, the old way of managing these systems, treating every server as an independent little box on a rack, is completely dead.
It has to be dead, purely out of necessity.
Oh, absolutely.
Yeah.
When you look at the PUE, the power usage effectiveness of these new AI factories, the thermal and electrical requirements are an existential challenge. If you are a DevOps administrator and you're trying to wrangle, say, 10,000 highly specialized compute nodes, you need an entirely new frameworks. You need a unified orchestration layer.
Because if you don't have that control...
If you don't have absolute granular control over every single watt of power and every single drop of coolant flowing through that facility, the facility simply cannot operate. It will physically exceed the capacity of the local grid, or it'll just thermally destroy itself.
Wow. Okay, so let's look at the first major pivot the industry is making to avoid hitting that wall at full speed.
Yeah.
We are seeing this massive aggressive shift away from traditional x86 processors toward Ampere-based ARM processors.
Yes, very aggressive.
You see hyperscalers, major telcos, dedicated AI data centers, they're all looking at ARM because the power consumption is radically lower. But we need to explain the mechanics here for you listening, because it's not magic. It really comes down to the fundamental architecture of how these chips execute instructions.
Right, it's down to the silicon.
So why doesn't x86 chip draw so much more power than an ARM chip doing the exact same math?
Well, to understand why the traditional x86 architecture has suddenly become, a massive liability in these specific AI and cloud-native environments, we have to look at the historical philosophy of chip design.
Okay, let's go back a bit.
The x86 processor is built on what we call a CISC architecture. That stands for Complex Instruction Set Computer.
Complex being the key word there.
Exactly. The philosophy there, which was developed decades ago when memory was incredibly expensive and really slow, was to make the hardware do as much complex work as possible with a single software instruction.
So the software sends one command, and then the hardware has to unpack it into this massive sequence of operations.
Precisely. The x86 chip has A highly complex physical decoder ring baked right into the silicon.
Oh, wow.
Yeah, so when an instruction comes in, the chip has to translate that complex instruction into smaller micro-operations that the execution units can actually understand. And that translation process requires a massive number of transistors to constantly fire.
And transistors firing means power.
Exactly. It's incredibly powerful and versatile, but having all those transistors constantly switching states draws a massive amount of power from the motherboard, and consequently, it generates a massive amount of heat. You are basically paying an electrical tax for the sheer complexity of the silicon.
Right, whereas ARM uses RISC, Reduced Instruction Set Computer.
Exactly. The philosophy is the exact opposite. A RISC processor strips away all that complex decoding logic.
It just dumps it entirely.
Pretty much. It focuses on keeping the number of available instructions minimal and highly standardized. It optimizes the execution of very simple, bite-sized instructions at just blinding speeds.
So it's doing simpler things, but way faster.
Right, because the hardware isn't trying to decode massive, variable-length, convoluted instructions. The physical circuitry on the chip is much, much simpler.
Which means fewer transistors.
Simpler circuitry means fewer transistors firing just to figure out what it's supposed to do. Less transistor activity means significantly less power drawn from the wall. And crucially, less power means drastically less heat that you have to actively remove from the rack.
You know, I was trying to think of a way to visualize this physical difference, and it's kind of like packing for a trip.
Okay, I like where this is going.
Using a RSC processor, the ARM approach, is like bringing a perfectly curated, hyper-efficient capsule wardrobe for a weekend trip.
Yes, exactly.
Like everything matches, every piece has a specific function. You only carry this small backpack, you breeze through airport security, and you exert very little physical energy. You get exactly what you need done with zero waste.
That's a great way to look at it.
But using an x86 processor is like packing your entire closet just in case you might need a tuxedo or, I don't know, scuba gear or snowshoes.
Right, you're ready for anything.
Yeah, you have a tool for literally every obscure scenario ever invented over the last 40 years of computing, and it's all jammed into one bag. But you are dragging this massive heavy trunk around, sweating through your shirt, burning massive calories just to get to the departure gate.
Yes.
You have all the capability in the world, but the energy expenditure to carry it is enormous.
That is spot on. And to take your capsule wardrobe analogy a step further, Bi-86 isn't just dragging the heavy trunk through the airport, it's paying exorbitant excess baggage fees on every single flight in the form of electricity.
Oh, man. The electricity bill is the baggage fee.
Exactly. The Bi-86 processor carries the physical legacy weight of backward compatibility. It has instruction sets for archaic computing tasks that a modern AI workload or a cloud-native microservice will simply never, ever use.
But the silicon is still there.
The silicon still physically exists on the die, and it still draws standby power, and it still needs to be cooled.
Which is wild when you think about the scale.
It is. When you multiply that power tax across tens of thousands of servers in a telco facility or a hyperscaler data center, you literally blow past the megawatt capacity of the local utility grid.
That's the brick wall.
That's the brick wall. You cannot build the data center because the local municipality cannot physically route enough power to your building.
But wait, if that's true, I have to challenge this logic a bit.
Go for it.
Because if ARM is so miraculously efficient, and if we are literally running out of electricity globally to power the AI revolution, why isn't this an overnight switch?
That is the big question.
Right. We know from the sources that the industry is only slowly adapting.
Yeah.
Why is porting applications such a massive bottleneck? Like if I'm a CTO building a billion-dollar AI factory today, why wouldn't I just buy 100% Ampere ARM servers, rip out all x86 and just be done with it?
Because software has momentum, and enterprise software momentum is incredibly hard to stop.
I mean, that makes sense, but how hard is it really?
It's fundamentally incompatible. Most enterprise applications, legacy databases, network function virtualization for telcos, and all these foundational software systems were written, compiled, and highly optimized explicitly for that Bi-86 architecture.
They speak the language of that heavy trunk.
Yes, they speak Bi-86. You cannot just take an application binary that was compiled for an Intel or AMD by 86 processor and drop it onto an Ampere ARM processor.
It just won't run.
The ARM chip will literally have no idea what to do with it. The instruction sets are fundamentally incompatible.
So you have to completely retool the software.
You have to port it. You have to rewrite underlying parts of the code, change the compilers, re-optimize the software for a multi-core RISC environment, and then, and this is the hardest part, rigorously, obsessively test it to ensure it behaves exactly as it did before.
Right, because you can't have downtime.
Exactly. When you are dealing with mission-critical telco infrastructure routing millions of phone calls or a financial hyperscaler processing high-frequency trades, recompiling and hoping for the best is not a valid business strategy.
Oh, absolutely not.
The testing and validation cycles take years.
Wow. So it's a massive integration headache. You essentially rebuilding the airplane while it's in flight.
It is a transitional nightmare for DevOps. So the physical reality on the data center floor is that even if an architect starts aggressively buying highly efficient 128-core Ampere-based ARM servers today to handle new cloud-native workloads, they still have massive fleets of legacy by 86 systems sitting in the racks right next to them handling the older enterprise workloads.
It's a mix.
It's a huge mix. They have AMD systems, they have Intel systems, they have specialized NVIDIA Grace Hopper compute nodes. You do not get a clean, homogeneous environment.
You end up with a highly complex, heterogeneous environment.
Exactly. A mixed bag of entirely different architectures that all need to be monitored, updated, and powered.
And that mixed bag is exactly why orchestration software has become the most critical layer in the stack. You have this chaotic ecosystem of different chips from different manufacturers, all speaking different architectural languages, all requiring different care and feeding, all drawing different power curves.
It's chaos without a management layer.
Right, and this is where Supermicro's SuperCloud Composer comes into play. It is designed to be the ultimate translator for this hardware chaos.
That's its primary mission.
SEC operates as an open, distributed infrastructure management framework. It is attempting to be the unified dashboard for every semiconductor manufacturer in the industry. AMD, Intel, NVIDIA, Ampere, all managed from one single pane of glass.
Which is a huge ambition.
But from an engineering standpoint, how on earth does software achieve that kind of unity when all these hardware vendors historically hate playing nice with each other? They all want you in their own walled garden.
Well, it achieves it by strictly relying on an industry standard called Redfish. SEC doesn't try to learn the proprietary management languages of every single hardware vendor.
Okay.
Instead, it harvests data from what are known as OpenBMC Redfish endpoints.
So for those of you managing these deployments, we know the baseboard management controller, the BMC, is the absolute lifeline. But let's look at how SEC actually interacts with it. Because, even if the main server CPU is halted or the operating system has completely kernel panicked, the BMC is just sitting there on the motherboard, completely independent, sipping standby power, keeping the out-of-band management alive.
Exactly. The BMC is a tiny, autonomous computer with its own processor, its own memory, and its own dedicated network interface.
It's like a computer within the computer.
It really is. It is the silent observer of the server. And Redfish is the modern, RESTful API standard used to communicate with that BMC.
How did we do this before Redfish?
Historically, the industry used older protocols like IPMI, which were clunky, often proprietary, and incredibly difficult to scale in modern software-defined environments. Redfish revolutionized this by using standard web technologies, HTTPS and JSON payloads, to expose the hardware's telemetry.
The documentation consistently refers to the BMC as the source of truth. It's not inferring what's happening. It knows exactly what's happening at the hardware level.
And that's exactly why SEC relies on it so heavily. SEC doesn't guess what the server is doing based on software logs.
Right.
It uses Redfish subscription services to directly query the BMC hardware. It sends an API call and essentially asks, what is the exact thermal state of your motherboard? How fast are your physical cooling fans spinning? What is the real-time wattage draw at the power supply? What specific firmware version is currently flashed to your network interface card?
It gets everything.
Everything. The SEC software acts as this giant, highly concurrent harvesting engine. It reaches out across the management subnet, pulls in all these rich JSON payloads containing attributes and metadata from these Redfish endpoints, regardless of whether the underlying compute chip is an AMD EPYC, an Intel Xeon, or an Ampere Ultra.
It doesn't care what brand it is.
It doesn't care. It normalizes all that distinct data and packages it into a unified, coherent dashboard experience for the DevOps operative.
I really want to emphasize to you, the listener, why this specific capability is so critical in the real world of data center management.
Yeah.
We are talking about the complete life cycle here, from day 0 to day 2 operations.
Absolutely.
Like day 0 is the initial planning, the physical racking, and the base network deployment. Day 1 is the massive configuration and provisioning stage. And then day 2 is the endless grinding reality of maintenance, performance monitoring, and security updating.
The day-to-day grind.
Right. And if you do not have a unified dashboard that normalizes this data, you fall immediately into the trap of severe vendor lock-in. If you buy Dell hardware, you are forced to use Dell's proprietary management software. If you buy HPE, you use theirs.
Which is a nightmare for procurement.
Right. Because if your procurement team sources servers from 5 different vendors based on supply chain availability, your DevOps team is suddenly forced to stare at 5 different monitors, utilizing 5 entirely different tool sets just to figure out why a single rack is overheating. SEC aims to completely eliminate that fragmentation by making the hardware layer essentially vendor agnostic from a management perspective.
It is the holy grail for a DevOps administrator. Having a single pane of glass to orchestrate a hardened, highly heterogeneous data center reduces operational friction exponentially.
How does it impact those day 2 operations we were talking about?
Well, think about a task as historically mundane but critical as updating a system BIOS or BMC firmware. Without a unified standard-based system, pushing a critical security firmware update across a mixed vendor fleet of 10,000 servers is a highly manual, highly risky, weekend-destroying endeavor for an IT operations team.
Because they have to do it differently for every brand.
Yes, they have to script different deployment packages for every vendor. But SEC, by utilizing Redfish, turns that into a streamlined, automated, scheduled task. It abstracts all the complexity of the underlying hardware.
Okay, but I've got to ask the cynical question here.
Let's hear it.
I look at this beautiful unified dashboard and I think,
Yeah.
is this a utopia that actually exists?
Oh, I see where you're going.
Right. If every massive chip maker out there, NVIDIA, Intel, AMD, if they fundamentally want you trapped in their specific, highly lucrative ecosystem, why would they ever voluntarily allow this? Why wouldn't they just lock down their BMCs?
It's a great point.
How does a standard like Redfish actually force these massive, hyper-competitive tech giants to play nice and expose their telemetry in a standardized format? Is it truly universal dashboard just a pipe dream?
It's a very fair, very grounded question.
Yeah.
And the answer is that the hardware vendors didn't do this out of the goodness of their hearts.
Obviously not.
No,
Oh,
the
no.
answer is that the massive buyers in the market physically forced their hand.
Follow the money.
Exactly. The hyperscalers, the Amazons, the Microsofts, the Googles of the world, they reached a level of purchasing power that allowed them to dictate the terms of engineering.
They became the boss.
They essentially turned to the hardware vendors and said, look, we are buying $100 million clusters. We will absolutely not buy your hardware unless it natively supports standard open management APIs like Redfish. We refuse to install your proprietary management bloatware on our networks. It just doesn't scale for us.
Wow. So they literally wouldn't buy it.
Right. So to win those massive defining contracts, every chipmaker and motherboard manufacturer had to adopt OpenBMC and Redfish standards. They had no choice.
That is fascinating.
Yeah, and Supermicro is brilliantly leveraging that hard-won open standard to build the SuperCloud Composer dashboard. The challenge for SEC today isn't actually extracting the data. The data is exposed. The challenge is organizing the absolute fire hose of metadata streaming from 10,000 BMCs into something a human administrator can actually comprehend and act upon without being completely overwhelmed.
Which brings us to what happens when you take that fire hose of Redfish metadata and apply it to the most advanced, dense, and frankly terrifyingly powerful AI hardware ever designed.
The NVL72.
Yes. The documentation dives incredibly deep into the anatomy of an AI super rack, specifically focusing on the NVIDIA NVL72 configuration. And this is where the entire management paradigm completely shifts on its head.
It really does.
Because in the old days, a rack was literally just a metal cabinet with rails. You discovered and managed individual 1U or 2U servers that just happened to be screwed into that cabinet.
They didn't really care about each other.
Right. But SEC does not treat the NVL72 as a collection of servers. It treats the entire rack as a single unified entity. It uses this tree architecture to map out and roll up the health of the entire system.
This is a crucial fundamental evolution to understand if you want to grasp where AI infrastructure is heading. The NVL72 is not a collection of independent compute nodes that just happen to share a metal box and a power feed.
It's not roommates.
Right, it's not roommates. It is a unified, highly synchronized AI supercomputer that happens to be so large it takes up an entire physical rack. The level of interconnectivity and integration is profound.
How does SEC visualize that?
When the SuperCloud Composer software discovers this hardware on the network, it maps it out using what it defines as rack slot units, or RSUs. It analyzes the compute trays, it analyzes the independent power shelves, it analyzes the ultra-high-speed networking switches, and it visually represents them in a cascading hierarchical tree structure.
Let's paint a picture for you listening of exactly what is inside these RSUs, because the specifications are genuinely mind-boggling.
They are staggering.
When we look at a single compute tray featuring NVIDIA Grace processors in this setup, we are talking about 72 compute cores and 124 gigabytes of memory per tray. And to be clear, that is not storage space.
No.
That is a full terabyte of high-speed RAM in a single ultra-dense compute tray.
In one tray.
Right. Then, mapped right below it in the tree, you have the dedicated power shelves manufactured by Lite-On Technology Core, providing massive, regulated DC voltage. And bridging it all together, you have the NVLink switch trays that allow all these individual processors across all these trays to talk to each other and share memory at blistering terabyte per second speeds.
It's an incredible engineering feat.
And SEC sees this entire massive topology as one interconnected organism.
It sees it, and crucially, it manages it holistically. What's absolutely fascinating from an operations perspective is how SEC handles firmware across this topology.
Okay, tell me about that.
So in a traditional legacy rack, if you had 72 independent compute trays, a DevOps admin would have to initiate 72 separate firmware update jobs.
Oh, that sounds awful.
It gets worse. They would have to ensure the power shelves were on the correct compatible firmware separately. They would have to update the networking switches separately, just hoping they didn't create a version mismatch that broke the whole cluster.
A total logistical nightmare.
Exactly. With the NVL72's tree architecture, SEC introduces true firmware bundling. You can stage a single, highly orchestrated, bundled firmware payload and push it to the entire NVL72 configuration atomically.
Wow. It's like the difference between managing a massive, sprawling apartment building versus managing a highly integrated, smart skyscraper.
I like that.
Think about it. In an older apartment building, if the plumbing fails on the 4th floor or the electrical panel blows in Unit 3B, the building manager has to go door to door, dealing with every single tenant and every single unit individually. They're completely separate, isolated ecosystems sharing a roof.
Right.
But the NVL72 treats the entire skyscraper as one giant integrated smart home. The thermal management, the power distribution, the computational brain, it all operates in absolute unison. You initiate one update command, and the entire building synchronizes and updates its infrastructure simultaneously.
That's a perfect architectural parallel. And those Redfish subscription APIs we unpacked earlier, they serve as the central nervous system connecting all those individual skyscraper floors back to the central brain of SuperCloud Composer.
So it brings all that data to the surface.
It provides the DevOps admin with a unified, instantly searchable asset list. They can see MMASI addresses for every network interface, exact serial numbers for every component, physical drawer heights in the rack, and aggregated health rollups.
That's a ton of visibility.
And it's actionable. It allows them to click a single icon in the graphical user interface and force a hard reset of a specific node, or blink the UID, the unit identification LED.
Blinking a light, that sounds a little, I don't know, trivial.
It sounds trivial, but when a field technician is physically walking the floor of a massive, incredibly loud, visually chaotic data center, blinking that blue LED allows them to spot exactly which compute tray out of thousands is failing and needs physical replacement.
Oh, I see. It's a lifesaver for the folks on the ground.
Absolutely.
But, and this is a massive, physically imposing but, when you treat an entire rack as a single multi-million-dollar computational brain, and you pack it top to bottom with NVIDIA Grace processors pumping out that level of computational power, the sheer amount of thermal energy generated is astronomical.
It is beyond what most people can fathom.
Right. Traditional data center air conditioning, where you blast freezing cold air down a hot aisle and suck it through the servers with high-velocity fans, it just won't cut it anymore.
Yeah.
It physically cannot remove the thermal mass fast enough. The physics of air cooling just completely break down.
They absolutely do.
Which leads us to the reality of keeping these systems from melting themselves down. the liquid-cooled reality.
This is the exact moment where the laws of thermodynamics violently assert themselves into the IT landscape. You literally cannot run an NVL72 or a D200 AI architecture on forced air cooling.
It's impossible.
The thermal density of the silicon is simply too high. The processors would hit their thermal junction limits and throttle to a halt or physically degrade in a matter of seconds. Air does not have the specific heat capacity required to absorb and transport that much energy away from the die.
Wow.
So the industry is forced to move to liquid cooling, specifically utilizing an in-rack CDU, the cooling distribution unit.
When looking at the SEC user interface design for this, it's remarkably stark. When you view a rack in SuperCloud Composer, if it has a CDU, there is a tiny, highly visible water droplet icon right next to rack slot unit 1.
Literal water droplet.
A water droplet, just to visually scream at the administrator, hey, be acutely aware, this specific rack is actively plumbed with highly pressurized liquid.
You can't miss it.
And SEC isn't just noting the presence of the CDU. It is pulling an insane granular amount of sensor data from this fluid loop.
What exactly is the software monitoring here?
It's continuously monitoring the vital signs of the rack's physical circulatory system. SEC pulls high-frequency, real-time data on the coolant return temperature. In a lab environment, you might see a reading of around 28.22 degrees Celsius, and it compares that against the coolant supply temperature to calculate the exact thermal delta.
So it knows exactly how much heat is being extracted.
Exactly. It is actively monitoring the mechanical pump valve pressure to ensure the fluid is moving at the precise required velocity. It's checking the volumetric flow rate in liters per minute. It is calculating the total aggregate heat load being successfully removed from the silicon in real time.
And it checks the dew point.
Mm-hmm.
That specific environmental detail really stood out to me in the sources. Why on earth does a highly advanced computational server rack care about the atmospheric dew point?
Because the laws of physics dictate that if the liquid coolant supply temperature drops below the dew point of the ambient air surrounding the server in the data center, atmospheric condensation will instantly begin to form on the exterior of the pipes and the metal cold plates attached to the processors.
Wait, you mean the hardware will literally start sweating?
Exactly. Sweating inside a rack filled with tens of millions of dollars of unshielded, high-voltage electrical components is a catastrophic resume-generating event.
Oh my God. A resume-generating event.
That's what we call it. So SEC constantly monitors the localized atmospheric dew point to ensure the CDU never, ever chills the fluid to a temperature so low that it causes that ambient moisture to condense into water droplets directly on the motherboard.
Which brings me to the absolute irony and, frankly, the latent terror of this entire engineering setup. Water, or any conductive liquid in highly sensitive server electronics, are natural, historical enemies.
Oil and water, literally.
Right. You spill a glass of water on your laptop keyboard, it's game over. It shorts out instantly.
Yeah.
Now, we are deliberately plumbing an entire skyscraper of the most expensive, highly constrained computer chips on Earth with highly pressurized fluid running directly over the CPU dies.
It sounds insane on paper.
It really does. Does plumbing an entire rack with fluid actually introduce a wildly greater risk of catastrophic failure? Or is the heat generation so extreme that data center architects literally have no other choice but to accept that massive risk?
It is entirely the latter. It is a forced hand dictated by silicon power density. I can assure you, data center architects and risk managers lose sleep over deploying liquid cooling at this scale, but they absolutely have no alternative if they want to run these AI models.
The heat is just that intense.
The power density of an AI superpod is simply beyond the physical limits of air-based heat exchange. Now, to mitigate that inherent terror you mentioned, SEC doesn't just passively monitor the temperature and hope for the best. It actively and aggressively monitors for leaks.
How does it do that?
The system architecture dictates that SEC collects sensor data from specialized leak detection sensors placed on the top and bottom power units at the CDU level.
And if it detects a leak? Like if a microscopic seal fails and a drop of coolant hits that sensor?
It immediately initiates a hard, automated shutdown condition.
It doesn't wait for a human.
No. If a leak is sensed, the orchestration software does not send an email alert and wait for a human operator to wake up, log in, and click a button. The physical stakes are entirely too high. It instantaneously triggers a predefined mitigation schema.
Wow.
It will attempt to gracefully, or if necessary, abruptly power down the incredibly expensive compute trays, halt the electrical current, and shut off the mechanical coolant flow to prevent short circuits, electrical fires, and permanent hardware destruction.
Mhm.
It is automated, ruthless self-preservation at the rack level.
Okay, so the liquid circulatory system is doing everything it can to keep the rack from physically bursting into flames. But cooling is just one side of the coin when it comes to keeping this massive brain alive and functioning. The other critical requirement is precisely controlling the massive amount of electrical power flowing into it from that overburdened utility grid we talked about earlier.
Right, the power routing.
If you are going to manage the electrical draw for an entire Ampere farm, you need intelligent power routing. You need incredibly smart power strips.
You need power distribution units, or PDUs, yes. And just like the server hardware itself, PDUs have evolved dramatically from simple electrical conduits into highly complex network devices.
So they aren't just power strips anymore.
Not at all. There is a very clear fundamental distinction in modern infrastructure between unintelligent PDUs and intelligent ones. An unintelligent PDU is basically what you have sitting under your desk at home.
Right, just a block of outlets.
It takes raw alternating current from the wall and physically splits it into multiple outlets. That's all it does. It provides raw, dumb power. If you want to know how much power a specific server is drawing on outlet 3, you can't. If you want to remotely turn off outlet number 4 because the server has locked up, you can't.
But the intelligent PDUs integrated to SEC are entirely different beasts. We see deployments utilizing devices like the Schneider Electric AP8641 intelligent PDU. They integrate this directly into the SuperCloud Composer dashboard.
Yes, and that integration is key.
They map it logically to a specific physical region of the rack, often designated as Location A. And SEC uses universal management agents to support a massive ecosystem of these power vendors. They aren't just supporting Schneider. They support Raritan, Eaton, Servertech, which was acquired by Legrand.
Right, because once again, the philosophy of SEC is anti-lock-in. Supermicro isn't trying to force you into only buying their branded power strips.
They want to manage what you already have.
Exactly. They want SEC to manage the massive, heterogeneous infrastructure investments you already have bolted into your racks. When you add a highly intelligent PDU, like that Schneider Electric model, into SEC, you suddenly gain immense granular electrical visibility.
What can you actually see?
You can see the active firmware version of the PDU controller itself, the exact serial number, and the real-time power input measured in precise watts. You can set critical lower and upper threshold limits for amperage draw to prevent tripping upstream breakers.
Oh, that's crucial.
It is. You can even monitor the CPU and memory utilization of the tiny controller inside the PDU itself. And most importantly, from an operational standpoint, a DevOps admin can remotely cycle the power physically cut and restore the electricity on a single specific outlet to hard reboot a completely frozen AI node without having to dispatch a technician to physically drive to the Phoenix data center and yank a power cord.
But all that incredible remote control requires a network connection to the PDU. And this is where we need to scrutinize the actual deployment practices.
Okay, let's get into it.
Because when setting this up, administrators assign an IP address, say 172.24.19 on the management subnet. And to communicate with the PDU, they often use SNMP community strings for read and write access, simple network management protocol.
Yes.
And this is where I need to raise a massive glaring red flag about human behavior in data centers. It is incredibly common during these day zero setups to see administrators using the absolute default public community string for full read and write access to the power infrastructure.
Oh, it happens all the time.
They know it's a security vulnerability. They will even say, we should probably change this from default later.
Using the default public SNMP string for write access on a core infrastructure device is the exact equivalent of leaving the master physical key to the bank vault hanging on a string from the front door handle. It nullifies all other security.
Exactly. But I have to ask about the reality on the ground. How often does this catastrophic oversight actually happen? Do massive, heavily audited AI data centers really leave the front door to their power infrastructure completely unlocked simply because an engineer forgot to go back and change a default password during the chaos of day zero setup?
Far, far more often than the industry would ever be willing to publicly admit.
Your kid.
I am completely serious. When a DevOps team is under massive executive pressure, tasked with physically racking, cabling, and deploying thousands of servers and hundreds of intelligent PDUs in a single week to meet a hyperscaler's launch deadline, corners inevitably get cut.
And SNMP is one of those corners.
Yes. SNMP relies on these community strings, which act essentially as plaintext passwords. If you leave the right access string set to the default public, anyone who can route packets to that IP address on the management network can send a trivial, unauthenticated command to the PDU to instantly turn off the physical power to a rack of AI servers right in the middle of executing a multi-million-dollar training run.
That is horrifying.
It is a devastating foundational vulnerability.
Which perfectly highlights why the other part of the security equation for SEC is so absolutely critical. You can't just secure the endpoints, you have to secure the management brains themselves.
The core nodes, yes.
The architecture requires setting up highly secure access for the SEC management nodes. Specifically, they deploy high availability, or HA cluster nodes, to ensure the dashboard never goes down.
Right. A standard robust deployment will configure multiple HA nodes, for example, HA node 0.114 and HA node 0.117 on the network.
So there's redundancy.
High availability simply means that if the primary management server experiences a catastrophic hardware failure, the secondary node instantly and seamlessly takes over the orchestration duties without dropping a single packet of telemetry.
But they have to talk to each other to do that.
Exactly. For those two distinct nodes to continuously communicate, synchronize their massive databases, and fail over securely, they need to be able to talk to each other automatically, constantly, without ever prompting a human for a password.
So they use SSH authorization keys, secure shell keys.
Yes.
But the setup process is remarkably manual for such an advanced system. The DevOps engineer has to open a terminal session, use a text editor like Nano to open the authorized keys file deep in the Linux file system, and literally copy and paste this giant, impenetrable block of cryptographic text from one node to the other.
It's very old school.
They save the file, and then they can instantly prove they can SSH from node 114 to node 117 and execute root commands without a single password prompt. Why is establishing this passwordless cryptographic entry so critical for the entire operation?
Because immense scale fundamentally breaks manual security processes.
Oh, so?
If you have an automated Python script running in SuperCloud Composer that needs to push an urgent zero-day security patch to 10,000 independent servers simultaneously, that automation script absolutely cannot stop execution and wait for a human being to manually type in a complex password 10,000 individual times.
It would take days.
It would take days, and it would fail half the time due to typos. SSH keys utilize public key cryptography to authenticate the machines to each other instantly, securely, and invisibly. It entirely eliminates the human bottleneck during critical, time-sensitive operations.
But the manual copy and pasting.
That manual copy-pasting of the key block in a terminal window, that is the gritty, unglamorous command line reality of day zero data center setup. It's tedious, it's prone to human error if you miss a character, but it establishes the absolute bedrock of secure, scalable automation.
Okay, so let's take a breath and look at what we've built. We have the physical metal mapped out. We have the high-pressure liquid cooling keeping the silicon from melting into slag. We have the secure intelligent power routed to the racks, assuming we actually change the default SNMP strings.
Hopefully.
Right? And we have the cryptographic keys exchanged between the management brains. Now, we finally get to the payoff. How does a single administrator actually take this sprawling, chaotic mess of physical hardware and logically organize it into a digital empire they can easily comprehend and control?
This is where it gets really cool.
This brings us to the operational phase. Day 0 to day 1, the DevOps map and device discovery. We are talking about utilizing pod view, which is essentially the signature defining feature of SuperCloud Composer.
Pod view is where the harsh physical reality of the concrete data center floor is beautifully translated into a logical software-defined map.
Because without a map,
if an administrator just have a flat spreadsheet list of 10,000 IP addresses, they have absolutely zero operational context. If a server at IP address 172.24.110.39 suddenly drops offline, does that matter?
you wouldn't know.
You wouldn't. Is it a critical Tier 1 database node processing financial transactions? Or is it a forgotten test machine sitting in a broom closet? Pod view provides that missing context.
The mapping capabilities are incredibly practical. An admin can create a pod, which is just a logical software grouping, and they can name it something highly specific, like the Ampere farm.
Right.
Then they start building out the digital architecture to match the physical reality. They specify the geographic location, the Phoenix data center. They create a digital representation of a rack in Building 6, Floor 1, which would be their fully managed rack complete with that intelligent PDU we discussed.
Exactly.
Then they can create another distinct rack representation on Floor 2, designated as an unmanaged rack. It's exactly like building a highly detailed digital twin of the actual concrete and steel building.
And once that digital twin architecture is built in the software, you have to actually populate it with the real servers. You have to find the physical hardware on the network and bind it to the digital map.
Right, the discovery phase.
That brings us to the critical process of device discovery. The SEC software needs to reach out across the network topology and find these brand new Ampere servers that the technicians just plugged in.
How does it find them?
There are two distinct, fundamentally different methods for accomplishing this discovery. The first method is highly structured, a ping spray.
Right, a ping spray is where you dictate a search across a specific contiguous IP range. You explicitly tell SEC, start scanning at IP address 172.24.19/39 and end at .121, and systematically knock on every single digital door in between to see if a BMC answers.
Exactly. It's systematic, it's highly controlled, and it generates a very predictable amount of network traffic. The SEC agent goes out, pings the address, and if an OpenBMC responds on the correct port, it instantly initiates a Redfish endpoint query to pull in all that deep hardware metadata we discussed earlier.
But there's a second method.
Yes. The second discovery method available is entirely different and, frankly, much more controversial. It relies on SSDP.
SSDP, Simple Service Discovery Protocol, also known as Universal Plug and Play.
Yeah.
The technical documentation notes that SSDP is actively enabled by default on all supermicro BMCs out of the factory.
Yeah.
Now, anyone who has ever spent time securing consumer home networking knows that Universal Plug and Play is incredibly notorious for severe security flaws in IoT devices.
Oh, it's famous for it.
It's the exact same chatty protocol that lets your smart fridge shout out across your home Wi-Fi to your smart TV, "Hey, I'm here on the network, look at me."
Yeah.
It is incredibly noisy, it relies on multicast broadcast storms, and it's entirely casual about authentication.
That's putting it mildly.
Are you seriously telling me that a protocol like that is turned on by default in highly sensitive multi-million-dollar AI factories processing proprietary models?
It absolutely is, and it perfectly illustrates the eternal, grinding tug-of-war in enterprise IT. The desperate need for fictionless scalability versus the inherent security risks of automated discovery.
So they just prioritize speed.
When a DevOps team is under the gun, tasked with racking, stacking, and provisioning hundreds of servers a day, they simply do not have the time to manually track, record, and type in every single assigned IP address into a spreadsheet to run a targeted ping spray.
That would take forever.
It would. SSDP flips the dynamic. It allows the server itself, the absolute moment it receives electrical power and a network cable link, to actively broadcast its presence to the management subnet. It completely removes the deployment friction. It allows SEC to instantly hear the device screaming its location, see it, and begin the registration and provisioning process automatically.
That's a security risk. I mean, if it's broadcasting to anyone who will listen.
The risk is substantial. If a bad actor or a compromised device gets access to that specific management VLAN, they don't even need to run a noisy port scan to find targets. They can just passively listen to those SSDP broadcasts and instantly, silently map out every single critical piece of infrastructure you have plugged in.
That's terrifying.
That is exactly why the deployment guides explicitly mention that if you do not want to use SSDP, you must manually log into each BMC and deliberately disable it. It's a fundamental architectural choice the security team has to make.
Speed versus stealth.
Exactly. Do you want the blistering speed of true plug-and-play during your day zero build-out, accepting the broadcast noise? Or do you want a completely silent, stealthy management network that requires slow, manual, highly targeted discovery? Most hyperscalers choose maximum speed during the initial deployment phase, rely on strict physical and VLAN segregation for security, and then lock down the protocols later.
Let's talk about the payoff, though. Let's look at what happens when SEC actually discovers these servers, because the sheer depth of the metadata it pulls is staggering.
It's a goldmine of data.
When discovering specific Ampere servers, say an ARS-210NE-FN, which is a larger 2U form factor, or an ARS-10YMNR, which is a dense 1U chassis, once discovered, the administrator can double-click on that server node in pod view and pull up what Supermicro calls the carousel view.
The carousel view is the ultimate realization of all this integration.
What do you see in there?
Without ever leaving the single pane of glass, without opening a new terminal window, the admin gets a deeply granular X-ray look inside the physical chassis of a server that might be located 3,000 miles away.
Just by clicking on it.
Yeah. They can see immediately that it's running a highly efficient 128-core Ampere Ultramax processor. They can look at the memory topology and see exactly which physical DIMM slots on the motherboard are occupied by Samsung DDR memory, drilling down to the specific part number, the clock speed, and the unique serial number of the memory stick itself.
They can see the NUMA regions, the non-uniform memory access layout, which is critical for optimizing how the software addresses that massive pool of RAM. They can see the UmpANSI addresses of every single network interface card.
All of it. And crucially, it's not just a read-only dashboard for viewing statistics.
They can take action.
Right from this carousel view, the DevOps admin has actionable icons. They can click a button to initiate a PXE boot and deploy a brand new operating system image directly to the bare metal. If the server is being decommissioned, they can execute a cryptographic secure erase of all the NVMe storage drives. Or if it's completely locked up, they can force a hard electrical reset through the BMC.
It's absolute control.
And that, right there, is the entire culmination of the SuperCloud Composer vision. We started this journey looking at the chaotic reality of a power-starved, multi-vendor data center running out of electricity. We navigated through the physical plumbing, the thermodynamics of liquid cooling loops, and the electrical routing of an NVL72 AI super rack. We mapped out the concrete floors of a Phoenix data center and populated it using automated discovery protocols.
And it all funnels down to one screen.
It all leads to this single point of execution. A DevOps administrator sitting comfortably at a single pane of glass, looking at a massive, efficient Ampere farm, and with a single click of a mouse, securely deploying a Tune operating system to a 128-core server. It is absolute, total lifecycle management, abstracting away all the underlying hardware complexity.
It really is a phenomenal engineering journey when you step back and look at the whole picture. We started this discussion by looking at that immovable brick wall, the global power grid crisis that is physically forcing the entire AI industry to rethink its silicon and pivot toward highly efficient ARM processors like the Ampere line to reduce the electrical tax.
Yeah, it's smashing the wall.
We explored how software orchestration layers like SuperCloud Composer use the Redfish API standard as the ultimate Rosetta Stone, translating the telemetry of AMD, Intel, and Ampere chips so they can all be managed harmoniously in one unified dashboard.
No more vendor lock-in.
We physically tore down the architecture of the NVIDIA NVL72 to understand how entire racks are no longer just metal cabinets, but are now functioning as single, hyper-integrated, liquid-cooled superorganisms, complete with automated dew point monitoring and instantaneous leak detection shutdowns to prevent catastrophic meltdowns.
The smart skyscraper.
Exactly. And finally, we saw how DevOps teams map out these massive digital empires using PodView, discovering these multi-million-dollar machines automatically. It's an incredible testament to human engineering and our ability to adapt to physical constraints.
It truly is.
But as we wrap up our deep dive today, I know you always have a final, broader thought to leave us with. What are you pondering after analyzing all this infrastructure orchestration?
Well, what truly fascinates me, and admittedly slightly terrifies me from a control perspective, is the ultimate trajectory of all this deep API-driven automation.
Okay, where's it going?
We've established today that these unified management dashboards are getting incredibly smart and that we're relying entirely on standardized Redfish APIs to comprehensively monitor and throttle massive AI power consumption, control pressurized liquid cooling loops, and execute hard shutdowns. Everything in the data center is now entirely software-defined and controllable via code.
That's true.
So here is the provocative thought I want you to mull over as you think about the future of AI. As the artificial intelligence models themselves become exponentially more capable of analyzing complex systems and writing code, what happens when the AI models running on these very racks are intentionally given permission to manage their own Redfish endpoints?
Oh, wow.
Will an AI, tasked with ruthlessly optimizing the speed of its own training run, eventually decide to automatically throttle its own power grid draw, redistribute its own liquid cooling flows to hotter nodes, and independently prioritize its own hardware workloads?
The AI managing its own cooling.
Are we simply building the highly responsive nervous system today for a physical data center that will eventually possess a mind of its own tomorrow, managing its own physical survival without any human intervention?
That is a massive concept to think about.
Uh-huh.
From hitting the brick wall of the power grid to building a data center that ultimately monitors and manages its own physical pulse. We'll leave you to ponder the implications of that one.